respects freedom. Our next speaker is Nicole. She's currently the CTO of Purism, and she has this role because she's been involved in embedded systems engineering for a long, long time, and now she will talk about how to make a phone that is actually truly free. Please give her a warm round of applause.
Yes, hello. Thank you very much for having me here. We have a lot of ground to cover, so please excuse me if I'm a little bit fast. So what I want to explain is a story that has different facets, and it's about a quest to create a mobile phone that respects users' privacy and users' freedoms, and that is really truly free. And I will explain what I mean with free. And it's also a story about a journey that we started over 2 years ago now, and which is still ongoing. Then, because making a smartphone or a mobile phone these days is incredibly hard, and that's also why it's called hardware. So the kind of freedom that I mean is the freedom not as in free market, but more as in freedom. And it's similar to what Paul explained just a few minutes ago, what he called sovereignty. What I call is more freedom. It's similar to the ideas of freedom that the Free Software Foundation has, which is the freedom to use it for any purpose that you like, to study it, to change it, and also to be able to share these changes. Because we at Purism and many others in the open source and free software communities, we believe that only if these are guaranteed, then a system can be truly trusted, and it really can be made in a way that it preserves the user's privacy. So to understand what the challenges are, you have to look at the mobile phone market, the current market. Every year, I don't know how many of you are aware of that, about 1.2 billion smartphones or phones are built worldwide. So this means that every 7 years, every human being on the planet Earth could have a new phone, which is really quite amazing. So what this also means is the mobile phone and smartphone market is gigantic. It's really huge. About 30% of all these smartphones, of those 1.2 billion, are made in just one single city, which is Shenzhen in China. So the largest wealth of experience in making mobile phones is in this location, which is also quite amazing. And this also led to this enormous experience and amazing experience that we just had while building the phone. We went to Shenzhen and asked arbitrary companies for our project to build this phone, and within half a day we got a quote for designing the PCB for our phone. And do this in the Western Hemisphere and Western world, engineers will ask the hell out of you. So this is totally amazing what is happening down there. They have the biggest experience and they are really fast to do things. Looking further at the market, you will quickly find out that the majority of the market is currently just governed and ruled by two major systems and two major companies, which is Google running the Android platform, which is about 85% of the overall global market, and Apple iOS, which is almost 15%. So basically, almost all the rest has run into insignificance. So that where we used to have Symbian and all these other different platforms, there are none these days. So it's mostly dominated by Android and Apple iOS. And this has a huge impact on the hardware market also. For making a phone, you need chips, and these chips are made by chipset makers. And there are quite a number of chipset makers worldwide. And also in the chipset market, there you can see a dominance of certain companies. And one of the major players here is Qualcomm. Qualcomm owns more than 40% of the smartphone chipset market currently. Then 20% about by Apple, 15% by MediaTek, which is also an Asian company, mostly Chinese, a little bit of Samsung, and then we have 15% others like Huawei and others. So there are only a very few companies actually creating these solutions. If you look inside just the Android ecosystem, because the Apple iOS system is pretty closed, inside the Android system, this ecosystem is dominated by just two, which is Qualcomm and MediaTek. And if you then think that 85% of the global market is Android, this means, in other words, about 2/3 of the smartphones that you find out there is just dominated by 2 or 3 companies if you count Google in, which is really, really amazing. So that's a huge market and very few companies actually ruling this market. But then there's not only hardware, but also the 3GPP standards. So if you want to introduce a device which runs on those cellular networks, you have to comply to those standards, and these standards are governed by the 3GPP organization, which is the Third Generation Partnership Project, in short 3GPP, is a standards organization which develops protocols for mobile telephony. These 3GPP specifications are in general open, so you can download and read them and try to understand them. It's huge. But they are not so free to use. And here we come into the pretty ugly area of patents, and especially software patents. And I will come in a moment to why this is all important. So 3GPP standards are covered by literally thousands of patents. And every new generation from 2G to 3G to 4G and now 5G, the number of patents grows almost by a magnitude. So we're talking about thousands of patents. And due to the patent legislation and the legal restriction, or the legal legislation for patents, a patent is granted in country or jurisdictions. And this is why we have about 80 million patents worldwide on 3GPP standards, and about 250,000 patents which are standard relevant. That means if you want to create something that runs on a cellular network which complies to the 3GPP standards, then it's about 250,000 patents for 4G, which are potentially in your way, or kind of in your way, which you have to use. And the largest patent holders are, in this order, basically Qualcomm, InterDigital, Ericsson, Nokia, Huawei, Samsung, and a few others. And the first 2 or 3 have more than 50%. And by coincidence, Qualcomm is also one of the #1 chipset makers, especially in the Android area. So this means we have a market which is controlled and dominated by very few companies. So why is this important? Because of this. The smartphone is used today everywhere by everyone. So it's a dominant platform everywhere on the planet and growing. Many people, or the smartphone has by far surpassed the relevance of ordinary computers. Many people have ditched their PCs traded this in for a smartphone or a tablet, and even tablets are now running out of importance. Smartphones are ubiquitous and universal, and yeah. So smartphones have become the platform, the computing platform of basically almost everyone's everyday life, and they store everything about us, our whole digital life. Communication, all means of communication, text, emails, voice calls, encrypted or not encrypted. Of course, also location, movement, everything. Secrets we store on our smartphones, like passwords or access tokens to almost everything, our bank accounts. So this is exactly why it matters to create something that we own, that we control, and like Paul said, that we are a sovereign of. Because this is our digital life that is controlled by these devices. And we entrust these to just a handful of companies. That's critical. So how to change this, and how to engineer a smartphone or a mobile phone? So the things you need is basically a CPU, which is in the embedded devices, usually an SoC, system on a chip, which controls memory, storage, RAM, things like that. It also drives the screen through GPU, IPU, and all these things. Controls the cameras and different peripherals, peripheral interfaces. So that's the main CPU. And then you also need those wireless interfaces that everyone currently expects from a smartphone these days, which is wireless Wi-Fi, Bluetooth, and of course the cellular modem. It's a phone. So you need a cellular modem for all the current technologies. This sounds kind of simple, but it isn't. So the main challenge in the smartphone is, first of all, the size. It is incredibly small, and everyone expects to be very, very small these days. And many of these components, the CPU, the SoC, and also the radios, consume a lot of power. And so this itself is a challenge. And this challenge is shared by all hardware manufacturers that want to make a mobile phone, which is also the reason why the chipset makers like Qualcomm, MediaTek, and the others have created solutions for that. And remember, the market is gigantic, so there's a huge demand, and the demand is, of course, answered by those manufacturers. And they created system on chips which integrate all of these things, including also the radios, onto one piece of silicon, which is perfectly neat and perfectly fine for many of those smartphones, very tightly integrated and conserving power and storage and all these things. But this has some problems. The advantage is that, for example, the cellular modem these days has become incredibly complex. And you have seen this, or I talked about this with the patent situation. There's a lot of knowledge that goes into developing the firmware for such a modem to control the radio and all the protocols that go on. So the modem firmware itself and controlling the radios is extremely complex, needs a huge firmware. And if you have it into the same SoC silicon, you can share a lot of the resources that you would usually just also use for your main CPU that drives your applications. So you can share the RAM, you can share the flash, and a lot of other things. And you also have fast data interconnection from your host CPU to this modem. So that's very convenient. Same saving, of course, also applies to Wi-Fi and Bluetooth, but it's less than with the cellular modem. So these 250,000 standard relevant patents in 3GPP 4G are pretty much not in vain because it's so complex. And you can see this also, if you look at the binary firmware of a cellular modem these days, these are usually 30 megabytes, just the binary firmware of these modems. So it's really huge piece of software, which then runs in your SoC and has access to the same RAM bus, for example, as your applications, which is a concern. As also Paul laid out, you're probably not sovereign of your own data anymore because the modem could spy on the RAM bus. And there was, fun fact, many of those modems actually run a Linux system. And there was a very good talk at the 33C3 by Harald Welter and Holger Freiter, which you can look at this URL. And they actually dissected one of those binary blob firmwares. And now, even if you wanted to do something like a free modem implementation, implement these 30 megabytes of binary thing and do this, it's really, really hard, because then you have to license all those patents. The 3GPP patents must be licensed. There is legislation for that by the patent holders under so-called FRAND terms, which means fair, reasonable, and non-discriminatory. But these patent holders still use the patents to control the chip market. And this also led to one of the lessons learned that we did when we first started out the research for doing our phone, that we learned that there are only very few, back in 2017, very few modem modules that you could buy which would actually allow you to make voice calls. Because at that time, modem manufacturers, especially a company called Qualcomm, wanted to sell their smartphone chips for smartphones that do actual voice calls. And they didn't want to sell modems to others to also do voice calls and build phones with that. So it was pretty hard at that time to find decent modem. And to have something customized for us, even that we're talking about 10,000 devices that we want to build, modem manufacturers like these wouldn't talk to us at all. So integrating a modem and asking for custom firmware or something like that for us at our size, even talking about 10K, not an option. And so here you see the grip through software patents from manufacturers on the market and what the market can actually do. So what we wanted, and now coming to the actual realization of what we do, is we wanted to create a phone and a smartphone which is binary blob free at runtime. That means that the host CPU does not have to handle any binary mystery code to download to any devices. We don't want to use any proprietary drivers, no closed source drivers, no closed source firmwares. And we wanted to have the radios, cellular, the Wi-Fi, Bluetooth, separated from the main CPU, also to reasons what Paul explained, to be sovereign over the data. And it should be based on free software only. We're striving to get Respect Your Freedom certification from the Free Software Foundation. And of course, it should be an open design, hackable for everyone. Schematics will be available to everyone without NDA. So it's completely, you can own it and you can change it and you can do whatever you like with that. What we came up in 2017 as the solution, and the best solution that we could find at that time, was to use the NXP i.MX8 quad as the main and host CPU, which features 4 Cortex A53 cores running at 1.5 gigahertz, not megahertz. We have enough peripheral interfaces for driving screens and cameras and all these things and all the peripherals needed, and also for sensors. But most importantly, the i.MX8 at that time was the only SoC that supported free drivers for the GPU, the graphics engine that drives the screen in the end, and which allows for graphics acceleration. And this is the GC7000 Lite from Vivante, for which there is a free software implementation driver, which is called Etnaviv, which is Vivante backwards. And for this, you have upstream mainline kernel drivers, and including the drivers also have been pushed upstream to Mesa already. And this is working pretty nicely already. Today, there are more choices. Unfortunately, now 2 years ago, they haven't been. Just to be fair, the Mali GPUs are also working quite nicely now, and also the port of the FreeDrano driver to the Adrenos GPUs of Qualcomm also become pretty much stable and available. What we also wanted to do is to have the radios separated out of the CPU so that they cannot interfere with the data that is stored on the CPU and the applications that are running on the CPU, on the main CPU. So we separated out the Wi-Fi and Bluetooth on an M.2 card, and this will also be implemented in this way in the final phone. M.2 is a pretty much well-known standard. It's connected using SDAO. The firmware sits on the card. The host CPU doesn't touch it. For the cellular 4G, we have 2 options, also sitting on an M.2 card. One is the Gemalto PLS8, which is made in Germany and partially in the US. The card will be made in the US. And also the Broad Mobi BM818, which is made in China. The Broad Mobi is available for more regions of the world, and that's why we chose the second one. And in theory, for the phone later on, any M.2 card that can use the same interfaces as we use them now and are supported in the firmware and in the hardware can be plugged into the device, and also other radios. If the antennas, of course, will be tuned for the 4G bands and for Wi-Fi and Bluetooth. And if you have another radio that you want to use on there, of course, just plug it in. For example, for these UHF radios that also Paul mentioned would be a possibility. And it will be very interesting to see. Now, what we also implemented in the hardware are hardware kill switches, so that you have a switch that really physically severs the hardware, like the cellular baseband, the Wi-Fi cameras, microphone, and also the sensors from the host CPU, so that even a malicious acting application cannot get access to this data and do some bad things for you, so your privacy can be really safely and secure. What we also did is we integrated a smart card reader so that you can use a smart card, like, for example, the OpenPGP card or arbitrary other smart card, to store your secrets in a very safe place, like encryption keys. And also the smart card reader, for this we have a separate project. We're collaborating with Werner Koch and Nibe Yutaka here for implementing a free firmware for this smart card reader, which is based on an STM32 L432KC, which is a microcontroller, and this will be accessible for everyone. So what we did in the first place is we started to create the development kit end of last year, and this is part of the PCB. I will show the real device in a few seconds. And this we did based on a so-called system on module, which implements all the heavy lifting for RAM and flash and all these things. And we designed the baseboard for that, so that we get something out, some hardware out, to developers that are interested in developing the software and helping with developing the software as soon as possible. And we started to distribute these at the end of last year. And this is the real hardware. Probably cannot really properly see the picture, but you can see the separated modules here for the modem and the Wi-Fi, and the system on module in the middle, and the phone screen on top. And this is actually working now. That's pretty nicely working. The software is making progress. And next, I can show you very proudly, this is the first boards that we just received from China. That's the first time that these are shown to the public for the final device, which has been developed in parallel in China, this location where they have this incredible, huge experience. And this is one side of the board, this is the other side of the board with the CPU in the middle, and you can also see the two M.2 slots on there, the GNSS module, and a lot of other stuff. So we are getting there, but hardware is hard. Everything takes much longer than anticipated, of course. And to give you an idea of the complexity of that board, we have on this board more than 160 different components, and that's over 1,200 parts placements on these boards. So that's an incredibly dense board. The PCB has 10 layers, so 10 layers of routing. The smallest parts are 0201 for the electronic geeks. The smallest ball pitch is 0.4 millimeter. That is the distance from one ball to the next of those BGA devices. The smallest diameter of drills and holes, for example, for vias, is 0.254 millimeters, which is incredibly small. And all of that is condensed onto a PCB, which is about the size of 2 credit cards. And this is what hopefully the final device, don't nail me down on those size numbers in the bottom right corner, but this is about the design that we intend to have in the end. So we're getting there. So this is the hardware part. On the software side, of course, as I already mentioned, we want to have everything open. Everything shall be free software on that. So everything what we do inside of Purism for the project will and is copyleft licensed, so GPL or LGPL v3, and all the contributions that we do to upstream projects, which are quite a lot, are of course according to the upstream projects. Our motto is upstream first. That is, if we can push our changes into the upstream projects, then we will definitely do so. This has several reasons. One of them, of course, is maintenance, but the other is, of course, also to avoid obsolescence of the platform and of the software. We want this software and this platform to strive and to live on. And this is only possible, at least in our opinion, when the things are mainlined. The bootloader, of course, of the system will not be locked in any way. It's a standard U-boot that also comes with the NXP CPUs and the BSPs for that. The U-boot will live in the eMMC of the board, which is the embedded multimedia card, which is similar to an SD card, but soldered onto the board. And we have one tiny issue, and this is where freedom is limited by the hardware, and today there's almost no way around it. For the DDR4 RAM, you need initialization somehow. DDR4 is pretty fast, and it's parallel signals on the board, so the attachment part that is inside the CPU has to very carefully tune the signal levels to talk to the DDR4 RAM. And there are a lot of patents on doing this. And this is also the reason why this DDR4 initialization sequence for almost no platform at all currently is open source. The DDR4 controller is a small microcontroller, and you have to download that firmware. I just mentioned it here. These are struggles that you have when you start to develop things. You suddenly find, oh, there's a piece of binary code that we have to use, and there's no way to avoid this. So we handle this by a second CPU that is also inside of the i.MX8. It's a Cortex M4 core, which then pulls this firmware out of an SPI flash and puts it into the PHY, and the PHY can initialize the DRAM, and we can continue to boot. But that's pretty stubborn, and I don't like that approach, but there's no way around it. The kernel that we're running is a mainline kernel. Currently, it's a 5.2.0 kernel. All the patches that we do, we are heavily working on the Vivante driver, and also a lot of other things trying to mainline all the drivers that are needed for the i.MX8. We're doing a lot of work that NXP should be doing, but well, we're doing that, porting all the stuff forward, and all the patches are sent upstream into the kernel community and get merged over time. Then on the operating system side, we're running a Debian derivative. So Purism also makes laptops, and on the laptops we have a Debian distribution which is called PureOS, and we're using the same PureOS basically just compiled for ARM64 on the phones too, which means you have the same packages and everything available on the phone that you're also used to on the laptops, which is pretty awesome. Which also means that you can install arbitrary Debian ARM64 packages on this phone. We also want soon to introduce Flatpak for application distribution. This has several reasons. One of them is, of course, the possibility to sandbox applications and to ease also application development, because dependencies can be handled a little bit smoother with Flatpaks and the Flatpak distribution. But this is still in the works. For the graphical user interface environment, we use a system based on Wayland, and we had to write our own compositor and shell on top of Wayland using WL roots, which is a toolkit to write compositors and shells. And these are called FOC and FOSH, phone compositor and phone shell. These are two of the very few parts that we wrote from scratch, because there was nothing that we could contribute to. For the application environment, we chose to go with the freedesktop.org standard, and we chose the GNOME approach, and we're using glib and GTK for application development for native applications, which works pretty nicely. And one of the reasons also to choose this approach is that we are now working very closely together with the GNOME community to enable GTK and GNOME applications and the whole GNOME environment to run smoothly on mobile phones, also using responsive design methods, so that applications that are written for the desktop can be made in a way that they also run on a small screen or smaller screen like on a mobile phone without having to reprogram or recompile them. And we're developing specialized widgets for that, and also all of this is going upstream. Currently it's in a separated library, but we're working with the GNOME community to accept this upstream. For those that are interested in participating or looking at this development, we have quite some development resources. Developer Purial SM Librem 5, this is the main site where the development, also documentation is stored. They can also find instructions how to download a virtual machine image for running on your laptop or PC, so that you can try the software on your PC without the device and also develop against this virtual machine, of course. Source Pure SM, this is the site where all the source code management and also continuous integration management happens. It's all in the public there. We work together with GNOME and with the kernel forks. Then here are some pictures of the actual applications. You maybe wonder how this actually could look like. And this is how it looks like. This is a modified version of the GNOME settings dialog. And here you can already see that on the left-hand side, you have the main menu of the GNOME settings, which now folds kind of in this responsive way into the different views of the different settings. On the right-hand side, you can also see the first implementation of a virtual keyboard here. And here are some other examples how to do this. So that's the initial setup, customized for the smaller screen, which then also works in the same way on desktop, which is pretty nice. Here we have the compositor and shell working, and it's not just the shell, it's really a shell on the right-hand side. Of course, you want to have a shell on a mobile phone. Here is contacts setting up, so a lot of things already working and being adapted. Here's a web browser. We use the GNOME web application for that, which is based on WebKit. On the left-hand side, there's a web page, the Purism web page in that case. On the right-hand side, you have the tab handling, how open tabs are handled in the browser, which is actually pretty neat. You can flick through the open tabs and do something. And now, this interesting time. Oh, we are running out of time, I'm afraid. But in general, I have a dev kit here, which is this thing. And in theory, someone could call it, but we don't have the time now to wait for that, I'm afraid. But it's working. So the whole software stack is running. We can do this later on. You can find me in the Chaos West village, and we can do this there if you're interested in. Now, summarizing a little bit of the challenges. So we have seen there's a lot of parts that we have to do to create this mobile phone. And a few of the major challenges are, of course, handling suppliers. Because if you want to do hardware, you have to work on all these suppliers and work with them to get the supplies, which is parts, PCBs, parts for the case, and all of that. This is an immense effort. So developing something is one thing, but getting all those suppliers in line is really a huge undertaking. Then the other part is, if you want to do something with consumer electronics and to put this into production and serious production and mass production, at the moment, there's almost no way around China. Because whole production facilities are there. They are the people that have the experience. They are the people who can crank out stuff really quickly and at a decent price. It's not cheap anymore, I can tell you, but it's at least a decent price. But it's very tough to work with China because of the language barrier. Only very few people speak English down there. So you always have those translators and interpreters in between. And this really makes collaboration really hard, additional to the time zone differences. And then also concerning suppliers, the component sourcing for an electronics product like this, and especially if you want to build 1,000 or 5,000 or even 10,000, you really get into trouble. We have, on some components, we have lead times of up to 20 weeks. So this means that you have to plan all your logistics way in advance before you start the mass production. And this is a huge challenge and undertaking. And then, of course, there are all those regulations and certifications, especially if you have an intentional radiator like the cellular phone or the cellular modem, which does radiate, of course, in certain frequencies. And to be compliant to all those regulations, that's a huge undertaking. You have to go to laboratories doing all those certification and things. So that's really challenging, especially for a company that hasn't done this before. The other challenge that we also see is that due to the lack of hackable hardware in the mobile space for the past years, because Android has become so dominant, there's only very little knowledge out there in the free software communities about these devices and how those base technologies that are needed for those devices can be done. And there's only very little free code out there. So this is also a big challenge and was a big challenge for us, and we are now working together with the different communities and empowering people, handing out those dev kits and trying to create this community, because we think that we must change this. We need to free this knowledge and enable the hacker communities to liberate people from this oligopoly of a very few corporations who currently run and govern our digital life. And clearly, at some point, they also exploit it. Just look at this Cambridge Analytica scandal. So, and with this, I want to close. We need power to the people, free the mobile, and hack the planet. Thank you very much.
Well, thank you for this great talk. So everybody, we have about 10 minutes for Q&A. You know the drill. There is a microphone angel somewhere in the middle. I literally can't see anything, but I swear he's somewhere there. And just wave at him or queue up behind him, and then we will get to you. And if you're on the stream, hop into the IRC or on Twitter, and then the signal angel can read aloud your questions.
There are people. Wow.
Do we have any questions from the audience? Yes? Okay, please go ahead.
Thanks a lot for your talk.
Welcome.
I think a big challenge is the application environment. I've heard that only China has more than 1 million Android application developers. And we need a lot of good applications on such a nice platform. What do you think about that? And maybe there is an option of running Android open source project or Sailfish OS on your platform. What do you think about it?
Okay, so that's, of course, one of the #1 questions. How do you want to handle applications? So, of course, first, this device is not intended to be the replacement of the average Android phone. So we don't expect to have those millions applications there. What we want to achieve is to create a platform that is conserving and respecting the user's privacy and also be secure. And for this, we only need a handful of really good applications, like a web browser, something that does the calls, handles messaging and all these things, the most basic applications. And what we also see in the community around the Librem 5 right now is that a lot of people are very interested in working for this platform and creating applications. Of course, we will not be quickly at this 1 million application or developer stage. No way, no. But we're getting there. And for the first time, or for the beginning, it will be dual use. You have your Android platform with different applications, and then you have this other platform, which is probably the Librem 5, which conserves your privacy and where it can be secure about your digital life. And probably at some point we can also talk about enabling running Android applications. There are some open source and free software projects about this, which could be possible. Sailfish, I'm not so sure if this works in parallel. We can support Qt applications in general, but a whole Sailfish, I don't know how this can be encapsulated.
Thanks.
Do we have another question? I think there's someone walking up. Please go ahead. Yes.
Hello. Thank you for the talk. This is a very exciting project. I was wondering if there's people running the development software on other devices, and if you're, if Purism is supporting that at all, or interested in having this not just be for the upcoming hardware, which does look cool, but there's a lot of old devices out there.
Yeah, of course. So you have to keep in mind that Purism is a quite small company. So supporting other projects is tough for us, but we do our very best. So if it's something that we can explain about things that we did, of course we're totally open to that. But of course the Librem 5 is currently the main driver for us. And this is also the thing, making hardware costs money, employing all those people developing this software stack, and also the hardware costs a lot of money, and we have to make some money. And this is why the Librem 5 is, of course, our main target, but anyone else can join our communities on the Matrix channels and get in touch with us. We do our very best, and we want this platform to be usable as widely as possible.
And now a question from the internet.
Yes. Is there any information on the cellular modem's firmware, a source available, user adaptable, or protected against updates by digital signatures?
That's a very good question. So the short answer is no, because we're dependent on module makers and modem makers that provide these modules and modems to us. And with the 10,000 devices that we're intending to make, we don't have much leverage on those modem makers. And so the firmware is binary only. We cannot do anything about it. We just can try to separate it as much as possible and to control the interface to the modem, but there's no much way to control the firmware itself. And this is also the reason why we have the separation and, the separation, yeah, sorry.
Okay, from the room.
Hi, thank you. That was a very interesting project, very noble intent. Hate to be the bean counter, how much are you expecting to charge for your devices? I'm not the right person to ask about finances. Currently, you can pre-order the phone right now from the Purism webpage, and if I'm not mistaken, it's $700 right now, $699.
Does anyone know? Approximately 700, apparently. Do we have another question?
Hi, thanks for the talk. I want to ask you some clarifications. I don't know if they 100% configure as the questions, but they could be answered as yes or no, so maybe I'll get away with it. Like, from what I understood, in the end, you settled down for IPs like CPU and GPUs and communications that were not open, right, in the sense of the schematics were available. And the other thing was, did you do the integration into SoC of the IPs by yourself, or did you have to subcontract it to people that maybe, because what I was interested in is if it's something that is doable with only open source tools. And the very last thing is the GPU drivers that you pointed out for the GPUs, are they reverse engineered open source implementations, or are they actually maintained by the vendors? I was wondering. Thanks.
Sure. So I hope that I got the question right.
a lot of the knowledge that we use to upstream the things and implement them in the kernel and into Mesa is based on the board support package that comes from NXP. So there are a lot of drivers there. Kind of free software. The problem with those BSPs, not only from NXP, is usually that they have a huge wealth of code which is not suitable for upstreaming. So what we do is we kind of cherry pick a lot of things from this vendor kernel and upstream this into the mainline kernel. And there are some other parts like the GPU driver that you also mentioned, which is closed sourced in the vendor kernel, the vendor distribution. This is a free software reverse engineering project, the Vivante project, which has already been going on for many years. Started with the IMX8, if I'm informed correctly. And that's a huge amount of effort to reverse engineer this. And by the first reverse engineering of the Vivante GPUs for the i.MX8, a lot of knowledge was gained so that the reverse engineering for the i.MX8, the GC7000 Lite that's in there, has been a lot easier and faster than it was for the i.MX6. So it's partially reverse engineering, partially using code that comes from the vendor kernel, porting this upstream. And yes, it's doable for experienced hackers from the open source community to dive into such a development project, but it's hard work, and you have to know a lot about hardware, internal workings of specific hardwares. For reverse engineering a GPU, you have to know a lot about OpenGL and Vulkan and all these drivers, how these work, to understand the binary and try to disassemble and understand how this works, and trying to develop this open source driver and integrate this into the kernel framework.
All right, a question from the front, I think.
Yes, thank you for the talk. You've shown in the beginning that the actual problem is not that much of a technical problem, but it's more like a political problem, that there are a couple of companies, most of them in China, that have actually a monopoly or oligopoly of the technology. So my question is, what must happen from a political point of view to solve this issue?
Oh dear. From a political point of view, it's very, very complicated, because if you start to rule into companies and try to tell them how they're supposed to work, it gets very, very messy very quickly. From a regulation political point of view, I don't actually know how to solve this problem. I think one of the, what politics could do is to much more support research efforts for developing these things at universities and in a free manner, to support free software communities to develop all these things. Let's say, for example, the RISC-V CPU core is an awesome platform for doing that, and for integrating a free GPU implementation into that, and for integrating all the other peripherals that are needed for those embedded devices. This would help a lot. And the other interesting part that politics probably could also do, and this is something that maybe amends to what Paul said, is to make it easier for communities and also universities and in general the ecosystem, let's say, to develop free radio protocols and access to radios, because those bands that are used for that are highly regulated. So it's very complicated to develop something in these bands, to develop a free implementation of a modem, for example, or some alternative to a cellular modem, or build a network which is alternative to the commercial networks. This would be a very good thing that politics could do, to deregulate some things, an area where we can freely live and hack and work.
All right. Do we have another question? Or do you want to use this last minute to accept a call on your phone?
We could probably, now it's off, I don't know why. It works perfectly well.
Now we're benchmarking the boot up time under stress.
Yeah, but we can do this later on in the Chaos West Village if you want to. It's pretty hot, so power management is still an area we have to work on.
All right, then please thank our speaker.